Welcome to another deep dive. Today, we're going to be venturing into the world of model theory.
Mm.
And you might be surprised to hear this, but we're focusing on how it's relevant to philosophy,
Okay.
not just math.
Interesting.
Our guide for this deep dive is the Stanford Encyclopedia of Philosophy.
Okay.
A pretty authoritative source in the field, wouldn't you say?
Absolutely. The Stanford Encyclopedia of Philosophy, or SEP as it's often called, is a constantly updated peer-reviewed resource.
Oh, wow.
It's really a goldmine of reliable information for all things philosophy.
So imagine model theory as this amazing tool that lets you use structures to understand the meaning of sentences.
Okay.
And by structures, we're talking about sets of objects and how they relate to each other.
Okay.
It might sound a bit abstract, but trust me, it gets fascinating.
What's really captivating about model theory is how it connects language to the world,
Okay.
or at least our mental representation of it.
Right.
It provides a framework for analyzing meaning in a very precise and rigorous way.
Okay, so let's try to ground this with an example.
Okay.
The SEP uses this scenario with a guy named Alfonso Arblaster and some pigeons.
All right.
You with me so far?
I am, and it's a great illustration.
Okay.
Imagine the sentence, he is killing all of them.
Okay.
By itself, it's just a string of words, right?
Right.
But if we specify that he refers to Alfonso and Polanem refers to the pigeons in his loft,
Okay.
the sentence suddenly gains meaning.
So it's like filling in the blanks.
Right.
We're creating a specific context,
Yeah.
a structure where Alfonso and the pigeons are the objects, and killing is the relationship between them.
Exactly. And if we were to discover that Alfonso actually did eliminate all the pigeons in his loft,
Oh, no.
that scenario would be considered a model for the sentence.
Okay.
The model makes the sentence true within that specific context.
Okay, so a model is like a real-world, or at least imaginable scenario
Right.
that fits the sentence.
Mm-hmm.
It's not just about the words themselves,
Yeah.
but about how those words connect to something tangible.
Precisely. And what's even more interesting is that we can have multiple models for the same sentence.
Right.
What if Alfonso only intended to eliminate the pigeons but failed?
Right.
Or what if there were other pigeons outside his loft that he didn't touch?
Okay.
These scenarios wouldn't be models for our original sentence.
So by looking at what is and what isn't a model for a sentence, we can get a much clearer sense of what this sentence truly means.
Right.
It's like exploring all the different ways it could be interpreted.
Exactly. And the Psyche points out that model theory uses 4 different kinds of definitions.
Okay.
Each shedding light on meaning from a unique angle. We'll definitely want to break those down.
That sounds like a plan. But before we go there, I'm already wondering how this all connects to arguments, the heart of philosophical debate.
A crucial concept we'll be exploring is model theoretic consequence.
Okay.
It essentially provides a way to test the validity of an argument by seeing if every model that satisfies the premises also satisfies the conclusion. It's a very powerful tool for philosophical analysis.
That's really intriguing. I'm starting to see how model theory could help us make our arguments more rigorous and precise.
Uh-huh.
But let's back up a bit and make sure we're all on the same page with the basics.
Okay.
Can you walk us through interpretation model and model theoretic truth in a bit more detail?
Of course, we touched upon interpretation with the Alfonso scenario.
Okay.
It's essentially assigning meaning to the elements of a sentence.
Right.
A model, as we discussed, is a specific interpretation that makes the sentence true.
Mm-hmm.
And model theoretic truth simply means a sentence is true within that particular model.
Right.
It's about grounding truth in a specific context.
Right. Like our sentence about Alfonso is only true if in that specific model he actually did what the sentence describes.
Exactly.
But you mentioned structure earlier.
Yeah.
And I admit I'm still a bit fuzzy on that. You said it involves sets of objects and their relations.
Yeah.
But could you give us a concrete example?
Let's stick with the pigeon scenario.
Yeah. Okay.
In model theory, we'd represent this as a structure.
Okay.
Our set of objects would include Alfonso and those unfortunate pigeons.
Oh.
Let's call them Percy, Penelope, and Paco.
Oh, no. Poor Percy, Penelope, and Paco.
Indeed, now the killing relation connects Alfonso to each pigeon, signifying that he eliminated them.
Right.
It's like a diagram with arrows pointing from Alfonso to each bird.
Okay, I can visualize that.
Yeah.
But what about these labels you mentioned?
Yeah.
What role do they play in the structure?
The labels are crucial because they link the sentence elements to objects and relations in the structure.
Okay.
So he would be linked to Alfonso.
Right.
Then would encompass Percy, Penelope, and Paco.
Right.
And killing would describe the action without labels.
Yeah.
It'd just be objects and arrows with no connection to the sentence.
So the labels are like bridges between the abstract language and the concrete model.
Mm-hmm.
They give the structure meaning in relation to the sentence we're analyzing.
That's a great way to put it. Now, the SCP mentions variations,
Okay.
like many sorted structures.
And indexing models with things like time, place, or even possible worlds.
Oh, okay.
These variations add layers of complexity to our models.
Whoa, hold on. Those sound pretty intricate before we get lost in the weeds. Could you unpack those a bit for us?
Certainly imagine a sentence like, one of those diseases is killing all the birds.
Oh, I.
In this case, we'd need a many-sorted structure with two distinct sets, one for diseases and one for birds.
Oh, okay.
Each set is a sort, and words like all would only apply within the appropriate sort.
Okay.
So all wouldn't mean everything in the structure, just every bird.
Okay, so it's like having different categories within the model.
Right.
It makes sense that we'd need that to accurately represent a sentence that talks about different types of things.
Precisely now, indexing models with time, place, or possible worlds is about accounting for context.
Okay.
Remember how the truth of our Alfonso sentence depended on whether he actually eliminated the pigeons?
Right? Yes.
We can make that time dependent by indexing the model with a specific time.
So the sentence could be true today, but false tomorrow if Alfonso gets new pigeons.
So indexing is like adding a timestamp or a location stamp to the model.
Uh-huh.
It acknowledges that meaning can shift depending on when and where things happen.
Exactly. We can even index with possible worlds to explore how truth varies across different hypothetical scenarios.
Wow.
It all depends on how much detail we need to capture the sentence's meaning accurately.
This is making me think about how much precision and nuance is involved in analyzing language,
Right.
and how model theory could be this incredible tool for philosophers to sharpen their arguments.
Yeah.
But before we jump ahead,
Okay.
the SCP also mentioned misinterpretations and non-standard models. What are those about?
Those are intriguing concepts.
Oh,
A misinterpretation is a model that makes a sentence true, but not in the intended way.
okay.
It's like assigning the wrong reference to terms, yet still ending up with a true statement.
Oh, okay.
A non-standard model is a specific type of misinterpretation that pops up in math, especially when dealing with infinite structures.
So a non-standard model is like a loophole, where a sentence can be technically true, but not in the way we usually think about it.
You could say that they exploit the limitations of language to create interpretations that are unexpected, yet logically valid. It gets a bit technical, but essentially they highlight how the same sentence can have multiple meanings depending on how we interpret the terms.
That's pretty mind-bending. I'm starting to see how model theory really pushes us to think critically about language and meaning anything else to cover before we dive into those 4 types of definitions.
One last point from the SP is the link between model theoretic semantics and Tarski's truth definition.
Okay.
You might remember Tarski from Logic.
Yeah.
He's famous for his definition of truth as snow is white is true if and only if snow is white.
Oh, yeah, that rings a bell.
Right.
It seems so obvious at first, but it actually provided a really rigorous way to connect language to reality.
Exactly.
Yeah.
Model theoretic semantics builds on Tarski's work by using models as a framework for understanding how sentences acquire truth values. Instead of saying a sentence is true if it corresponds to reality, we can now talk about it being true within a specific model.
So we're adding a layer of context to truth.
Uh-huh.
It's not just about whether a sentence matches the world in general, but whether it matches the world as represented in a particular model.
Precisely. This shift is subtle, but incredibly important. It allows us to analyze truth in a more nuanced way, taking into account different interpretations and contexts.
Wow, this is already so much to process, and we've just scratched the surface. I'm ready to dive into those 4 types of model theoretic definitions whenever you are.
All right.
Let's do it.
Cool.
Sounds good.
Great.
All right, let's delve into those 4 types of model theoretic definitions, each offering a unique way to use models to unlock the meaning of language. The first one we'll explore is defining classes of structures.
So instead of defining individual words or concepts, we're defining whole categories of structures. That sounds ambitious. It is, but model theory provides the tools. Remember how a sentence divides all its possible interpretations into those that are models and those that aren't. It's like drawing a line separating the structures that make it true from those that don't.
Yes, I remember it's like the sentence sets up a membership test, and only structures that pass get into the club.
That's a good analogy, and that dividing line is what defines a class of structures. The class includes all the structures that satisfy the sentence, all its models.
Okay, I'm with you so far, but can we make this a bit more concrete?
Mm-hmm.
I'm a bit of a hands-on learner. You know.
Of course, the SCP uses the legal definition of a trust as an example. It involves those labeled 4 typals we discussed earlier, like the one with Alfonso the derelict land and the other 2 individuals.
Yes. Alfonso is back. I remember those four tuples. Each one represented a specific way those four elements could be related.
Exactly. The sentence defining a trust picks out a specific class of those four tuples, only those where the first person transferred property to the second person who holds it for the benefit of the third person.
So any four-tuple fitting that description would be a model for the sentence, this is a trust. And all those models together form the class of trusts. It's like a blueprint for identifying a trust in any given situation.
Precisely. And this process of defining classes using sentences is called axiomatization. It's about establishing rules that all members of the class must follow. Instead of listing every single instance of a trust, we define the underlying structure that makes something a trust.
So it's more about defining the essence of a concept rather than just giving examples. That seems very relevant to philosophy, where we're always trying to get at the underlying nature of things.
Absolutely. The ETI offers a great example from mathematics, the definition of abelian groups.
Hmm.
It highlights how this process works in a more formal setting.
Okay, abelian groups, math is not exactly my forte, but I'm willing to give it a shot.
An abelian group is essentially a set of objects with an operation usually called addition that follows certain rules. The order you add things in doesn't matter. There's a neutral element 0 that doesn't change anything when added, and every element has an inverse.
All right, I vaguely remember those rules from somewhere. So how do we axiomatize the class of abelian groups?
We use axiom sentences that express these rules formally. These axioms use symbols like plus for addition 0 for the neutral element, and variables like x and y to represent any object in the group.
So the axioms would be like x plus y equals y plus x to show that order doesn't matter when adding.
Precisely, we'd have other axioms for the other rules, like the existence of an inverse for each element. Any structure satisfying all these axioms would be an abelian group.
I see. So we're creating a kind of logical blueprint for what it means to be an abelian group. Any structure that matches the blueprint is automatically a member of the club.
Exactly. It highlights the power of model theory to define not just individual structures, but the fundamental properties that make them belong to a specific class.
The SP mentioned a three-level pattern in these axioms. Can you explain that?
Ah, yes, you have logical symbols like equals and the for all symbol, which have fixed meanings. Then there are non-logical constants like plus and 0, whose interpretation comes from the specific structure. Finally, variables like x and y represent any object in the structure's domain.
So it's like a hierarchy of symbols, each playing a different role in defining the class. It seems like that level of precision could be really useful in philosophy, where we often get tripped up by vague or ambiguous language.
Indeed, model theory provides tools for greater clarity and rigor in defining concepts, which can be very helpful for philosophical discussions. However, it's important to remember that not every philosophical concept lends itself easily to this kind of formalization. Some concepts are too context-dependent or nuanced to be captured by a set of axioms.
That makes sense. It's like trying to define love or justice with mathematical precision. It's just not going to capture the full richness of those concepts.
Exactly. But even in those cases, model theory can still be helpful for analyzing the structure of concepts and the relationships between them.
Okay, so we've covered defining classes of structures. What about that second type of definition, defining relations within structures? How does that work?
Instead of defining an entire class of structures, we focus on specific relationships within a given structure. And think of it like zooming in on a particular detail of the model.
So instead of defining trust in general, we might define the specific relationship between the trustee and the beneficiary within a particular trust.
Exactly. We use formulas with free variables for this. Remember how we use variables like x and y in the abelian group axioms to represent any object in the group?
Yes, they acted as placeholders for any element in the structure.
In formulas defining relations, those are free variables because they're not bound by quantifiers, like for all or there exists. This means they can take on different values within the structure, allowing us to explore various relationships.
Okay, I think I see where this is going. By plugging in different values for those free variables, we can see which combinations satisfy the formula and which don't.
Precisely. And those combinations that satisfy the formula define the specific relation within the structure.
Can you give us a concrete example? My brain is craving one right about now.
Certainly, let's consider the circle equation from geometry x squared plus y squared equals 1. Remember that one?
Vaguely, it had something to do with the radius in the center of the circle, right?
Right. In this equation, x and y are our free variables. If we're working within the structure of real numbers, we can plug in different values for x and y to see which pairs satisfy the equation. For example, 0, 1 works, but 2, 3 doesn't.
So the circle equation, with its free variables, defines the relation of being a point on the unit circle centered at the origin. It acts like a filter, selecting only those points that fit the criteria.
Exactly. Any pair of numbers satisfying the equation corresponds to a point on that circle. That's how we use formulas with free variables to define relations within structures. It allows us to pinpoint specific connections and patterns within a given context.
That's fascinating. I never thought about the circle equation as a definition of a relationship, but it makes perfect sense. It's like a code that reveals a hidden pattern within the structure of numbers.
That's a great way to think about it. And this concept is incredibly useful in mathematics, particularly in areas like geometry and algebra. It allows mathematicians to rigorously analyze complex relationships between objects.
Okay, so we've covered defining classes of structures and defining relations within structures. What about that third type interpretation? How does that fit into all of this?
Interpretation is about building new structures from existing ones, using definable relations and functions. It's taking the building blocks from one structure and rearranging them to create something new. It might sound abstract, but it has some powerful applications.
Can you give us an example? I'm all about those concrete illustrations.
Of course, the SAP uses the example of interpreting the group of integers in the structure of natural numbers.
What a group of integers, structure of natural numbers. My math anxiety is starting to flare up.
Don't worry, we'll take it step by step. The natural numbers are simply the counting numbers, 0, 1, 2, 3, and so on. The integers include the natural numbers and their negatives, -1, -2, -3, and so on. And a group, as we discussed earlier, is a set of objects with an operation that follows certain rules.
Right, like our abelian group example. But how do you interpret the group of integers within the structure of natural numbers, it sounds like, trying to fit a square peg in a round hole?
It might seem that way, but it can be done. The trick is to represent each integer as a pair of natural numbers.
A pair of natural numbers. How does that even work?
Think of it like this. We can represent the integer 3 as the pair 4, 1, because 4 minus 1 equals 3. Similarly, we can represent -3 as 1, 4, because 1 minus 4 equals -3.
Ah, I see. We're using subtraction of natural numbers to represent addition of integers. It's like a clever coding scheme.
Exactly. We formally define an equivalence relation on pairs of natural numbers, grouping together all pairs representing the same integer. For example, 4, 1, 5, 2, and 6, 3 would all be in the same equivalence class representing the integer 3.
So each equivalence class corresponds to a unique integer. It's like bundling together all the pairs that mean the same thing.
Precisely, this set of equivalence classes, along with a suitable definition of addition, forms a structure isomorphic to the group of integers.
Isomorphic, now there's another word I haven't heard in a while.
Isomorphic means the two structures have the same essential properties, even though they might appear different on the surface. It's like having two maps of the same city. They might use different symbols and colors, but both represent the underlying layout of streets and buildings.
So we're basically creating a new map of the integers
Yeah.
using the language of natural numbers.
Yeah.
It's like translating one system into another while preserving its core structure.
That's a great way to put it. This technique of interpretation has some fascinating applications, particularly in the philosophy of science.
Oh, I'm always interested in those interdisciplinary connections. Tell me more.
Philosophers of science have explored using interpretation to clarify the idea of theory reduction. If you can interpret one theory within another, the first theory can be considered reduced to the second.
So it's like saying one theory can be explained in terms of a more fundamental theory. It's like finding a deeper level of explanation.
That's the basic idea, but real-world theory reduction is usually much more complex than the simple model-theoretic notion captures.
That makes sense. Reality is rarely as neat and tidy as our theoretical model still. It's fascinating to see how these abstract concepts from model theory can shed light on real-world issues in the philosophy of science. It's like we're finding unexpected connections between seemingly disparate fields.
Absolutely. Model theory offers a powerful lens for analyzing a wide range of philosophical questions, from meaning and truth to the relationships between different theories.
Okay, we've tackled three types of model theoretic definition so far: defining classes of structures, defining relations within structures, and interpretation. What about that last pair, implicit and explicit definability? The CP article was a bit brief on those.
Those are a bit more technical, so we won't go into too much detail here. Essentially, they deal with whether a relation can be defined using a formula in a particular language.
So it's like asking if the language has the vocabulary to express that specific relationship. Like some languages might have words for concepts that other languages don't.
That's a good analogy. Implicit definability means the relation can be uniquely characterized by a set of formulas, even if we can't write a single formula that defines it directly. It's like describing something indirectly through its various properties. Explicit definability, on the other hand, means we can define the relation directly using a formula.
I see. So it's about whether we can pinpoint the relation directly or whether we have to circle around it with a set of indirect descriptions.
That's a good way to think about it. And interestingly, the SIP mentions historical confusions surrounding the term implicit definition. Early mathematicians used it differently than model theorists do today.
Ah, the ever-evolving nature of language. It seems like every field has its own jargon that can trip up outsiders. Thanks for clarifying those concepts for us.
My pleasure. Now, are you ready to move on to the next major topic, model theoretic consequence? This is where we see how model theory can really help us analyze arguments in philosophy.
Definitely. I'm eager to see how all of this connects to the way we think about logic and reasoning. All right, model theoretic consequence. This is where we connect model theory to the heart of philosophical reasoning. I'm ready to see how it works.
It's a powerful tool for understanding how conclusions follow from premises.
Okay.
It essentially tells us that a conclusion is a logical consequence of a set of premises, if and only if every structure that satisfies the premises also satisfies the conclusion.
So it's like a universal test for validity. If we can find even one structure where the premises are true, but the conclusion is false, the argument crumbles.
Exactly. It sets a high bar, modern logic message. Textbooks often use this model theoretic consequence relation to determine validity, a shift from older methods that relied on specific syntactic forms.
That seems much more precise than trying to fit arguments into predetermined categories. But are there any limitations to this model theoretic approach?
There are. While it's great for checking validity, it doesn't always capture the full picture. Sometimes an argument might seem invalid by this strict definition, but there could be deeper conceptual links between the premises and conclusion that the model theoretic analysis misses.
So it's possible to have a valid argument that doesn't pass this model theoretic test that seems a bit counterintuitive.
It can happen. That's why conceptual analysis is still vital in philosophy. We need to carefully examine the meanings of terms and the implicit relationships between them to fully grasp the logical connections in an argument.
So model theory is a powerful tool, but not a replacement for good old-fashioned philosophical thinking.
Right.
We need both to make sense of complex arguments.
Precisely the CPP highlights this with the argument, there is a father, therefore there is a child.
That seems obviously valid. How would model theory handle that?
If we try to represent it directly using quantifiers and predicates like there exists X such that X is a father implies there exists X such that X is a son, where Fx means X is a father and Sx means X is a son. We can't prove it model theoretically.
Because we can imagine a model with a father who, for whatever reason, doesn't have a child.
Exactly, but we intuitively know the argument is valid because of the concept of fatherhood being a father implies having a child.
So to make the argument work model theoretically, we need to go beyond the surface level of the sentences and build that implicit relationship into our model.
Precisely. We need to analyze the underlying conceptual structure to capture the true logical connections, not just the formal structure of the sentences.
That's a great reminder that philosophy goes beyond symbol manipulation. We need to grapple with meaning and concepts.
Absolutely. Model theory can aid in that process, but it's not a substitute for careful philosophical analysis.
Okay, so model theory helps us analyze arguments. What other insights does it offer?
The CPP article delves into expressive strength, which is all about comparing the power of different languages to express certain concepts. Some languages are better equipped to capture certain ideas than others.
So it's like how some languages have words for concepts that just can't be translated directly into other languages, like Schadenfreude in German?
That's a perfect analogy. Formally, one language is reducible to another if every class of structures definable in the first language is also definable in the second. The second language is at least as powerful as the first.
Like it has a bigger vocabulary or more flexible grammar to capture a wider range of ideas.
Exactly. A classic example is comparing first-order logic to the language of syllogisms, those all A or B type statements.
Ah, syllogisms. They felt pretty limited in what they could express.
They are, and model theory can prove that first-order logic is strictly more expressive.
Oh.
We can write sentences in first-order logic that simply can't be expressed using only syllogistic forms.
So first-order logic is the heavyweight champion in that matchup. But how do we actually determine the expressive strength of different languages? That seems like a tricky task.
It can be, but model theory offers tools like back-and-forth games.
Back-and-forth games, that sounds more like something you'd play at a party than in a logic seminar.
I know, right? But these are sophisticated mathematical tools for comparing expressive power. They involve two players. Spoiler and duplicator taking turns picking elements from two structures.
So it's a game of strategy where each player is trying to outwit the other.
Exactly. The outcome reveals whether the two structures can be distinguished by a sentence in a particular language, if spoiler can always win. The language can differentiate between them. If duplicator can hold her own, the language is too weak to tell them apart.
It's like model theory is turning logic into a game. But why are these games so useful for understanding expressive strength?
Because they're flexible and general, they work with various types of structures and even different types of logic beyond first-order logic. They provide a unified framework for comparing how much different languages can say.
So it's a universal tool for assessing the power of language that's quite elegant.
You could say that, and these games have been crucial in major model theory results, like Lindström's theorems.
Lindström's theorems, those sound important. What are they about?
They characterize first-order logic in a surprisingly simple way. They essentially state that first-order logic is the strongest logic that satisfies two specific properties:
Okay.
the downward Leeuwenheim-Skolem property and the compactness theorem.
Okay. I'm going to need a bit of help with those. They sound pretty technical.
Of course, in simple terms, the downward Leeuwenheim-Skolem property means that if a sentence has an infinite model, it also has a countable model. That is a model where the objects can be put into a one-to-one correspondence with the natural numbers.
So it's saying that even if a sentence is true in a vast infinite structure, it must also be true in a smaller countable structure. Interesting.
Exactly. And the compactness theorem says that if every finite subset of a set of sentences has a model, then the entire set has a model.
So if every little chunk of the puzzle fits together, then the whole puzzle must fit together somehow.
That's a great analogy. These properties might seem technical, but they have profound implications for the expressive power of first-order logic.
I'm starting to see that. So Lindström's theorems tell us that first-order logic strikes a balance. It's expressive enough to capture a lot, but not so powerful that it breaks these crucial properties.
Precisely, and this balance is key to fascinating applications like Robinson's non-standard analysis.
Non-standard analysis. I think my math vocabulary is officially exhausted.
Don't worry, it's a really cool way of using model theory to make sense of infinitesimals, those infinitely small quantities that Leibniz used in developing calculus.
Infinitesimals, I thought those were just a mathematical myth.
For centuries, mathematicians struggled to fit them into the standard framework of real numbers, but Robinson showed that you can use model theory to construct a system that includes both real numbers and infinitesimals.
So he found a way to make these mythical creatures mathematically real. That's incredible.
It is, and non-standard analysis with its infinitesimals can prove theorems in standard calculus. It's like taking a detour through a strange landscape, but ending up at your destination with new insights.
This is mind-blowing. It seems like model theory is opening up new dimensions in mathematics.
It is, and it raises philosophical questions about the nature of mathematical objects and the relationship between different mathematical systems. It pushes us to think about the foundations of math in a whole new light.
We've covered so much ground today, from basic definitions to the expressive power of languages and even non-standard analysis. But the SIP article mentioned the distinction between models and modeling that we haven't discussed yet. What's that about?
It's an important distinction because the word model has multiple meanings. Even within model theory, we've used it in several ways: a structure that satisfies a sentence, a representation of a phenomenon, even a mental representation. It's easy to conflate these meanings.
I see what you mean, and that's not even considering all the ways model is used in science, art, and everyday language. It can definitely get confusing.
Exactly. So how do we make sense of this? The set provides a historical overview of how the word model evolved from its origins as a measuring device to its modern use in representing complex systems.
So originally a model was a physical object used to understand something else, like a miniature building or a scaled-down solar system.
Precisely over time, this broadened to include abstract representations like equations and formulas.
So that's how we arrive at the model theoretic model as a set theoretic structure, representing relationships between objects. It's like a more abstract version of those early physical models.
Exactly. In both cases, a model represents something else, a phenomenon, a system, a set of ideas.
So the difference between models and modeling lies in the focus, the representation itself, versus the process of creating and using representations.
You got it. Modeling is the activity of building, testing, and refining models to understand the world.
So scientists, engineers, artists, even philosophers engage in modeling when they create representations to explore and explain things.
Absolutely. And model theory, with its precision, can be a valuable resource for this broader activity of modeling it offers a framework for thinking about representation in a rigorous and systematic way.
This is illuminating. It highlights how pervasive models are in our thinking and how crucial it is to be clear about what we mean by model. Before we wrap up, I'm curious about the philosophical questions the CEP article mentioned arise from model theory. Can you give us a taste of those?
Model theory has deep implications for how we think about language meaning truths and even the nature of reality.
That sounds profound. Can you give us some specific examples?
One area is the relationship between language and the world. The concept of reference, how words connect to objects and properties, is central to both model theory and philosophy of language.
So model theory can help us understand how we use language to talk about the world. It's like a bridge between language and reality.
Exactly. It also raises questions about the limitations of language. The fact that different structures can satisfy the same sentences challenges the idea that language uniquely captures reality.
It's like saying there might be multiple ways of understanding the world that are equally consistent with our language. That's a humbling thought.
Indeed, this connects to the concept of isomorphism, two structures with the same essential properties, even if made of different objects.
Like those two maps of the same city.
Exactly. Isomorphism raises questions about identity. Are two things the same, even if they have different parts? It pushes us to think carefully about what it means for things to be identical.
Those are deep philosophical waters. Any other areas where model theory challenges our assumptions?
The concept of indiscernibility is another. Two objects are indiscernible if no formula in the language can distinguish them.
So they're like perfect twins, at least from the language's perspective.
Exactly. This raises questions about individuality. Can two things be truly unique if they're indistinguishable in every way our language can express? It challenges us to think about the nature of identity and difference.
This has been an incredible journey. Model theory has implications far beyond what I initially imagined.
It's been a pleasure exploring these ideas with you. If you'd like to delve deeper, the CEP article recommends books by Button and Walsh and Baldwin. They offer rich insights into this fascinating field.
I'll definitely check those out. Well, this has been another deep dive. Thank you so much for joining me on this exploration of model theory.
My pleasure.
And to our listeners, keep questioning, keep exploring, and keep diving deep.